Hello everyone, we just got some huge updates about 3I Atlas, and Harvard scientist Avi Loeb has just released new calculations that once again make us question the true nature of this object. So let's first talk about the anti-tail. 3I Atlas has this massive jet that points directly toward the sun. Now, here's what makes this so weird. Normal comet tails always point away from the sun. That happens because of solar wind and solar radiation pressure. The sun is basically blowing everything backward like a giant leaf blower. For a jet to point toward the sun and push against that wind is already unusual, but for that jet to extend hundreds of thousands of kilometers while staying tightly focused in a narrow beam is something we have never really seen before at this scale. Back in July, when Hubble first captured images of this object, the anti-tail was already visible. In September, it was still there. In November, after the object passed its closest point to the sun, it was still stretching toward the star. And in December, astronomers captured images showing this jet extending for hundreds of thousands of kilometers in the sunward direction. So this structure has persisted for at least 6 months through thousands of rotations and through massive changes in temperature and solar heating as the object passed perihelion, and the whole time it stayed pointed at the sun. Now, here is the key question. What is this anti-tail actually made of? When ice on a comet sublimates from solar heat, it turns into gas. That gas shoots away from the surface. As the gas flows outward, it drags dust particles along with it. So, the anti-tail could be made of gas molecules streaming sunward, or it could be made of dust particles that got launched sunward but are now coasting on their own momentum after the gas stopped pushing them. Or it could be both, gas and dust traveling together. This distinction is absolutely critical because it tells us whether 3I Atlas is behaving like a natural comet or doing something that natural physics cannot explain. So Avi Loeb did the actual calculation to figure out how far gas can travel before it gets stopped. But first, please take a second to help me out by clicking the like button. So the answer comes down to a balance between two opposing forces. On one side, you have the gas shooting out from 3I Atlas. This is the thermal speed you would expect from carbon dioxide molecules turning from ice directly into gas when heated by the sun. On the other side, you have the solar wind. The solar wind is this constant stream of charged particles flowing out from the sun. At the distance where 3I Atlas is right now, about 2 astronomical units from the sun, the solar wind is moving at about 500 km/s. Think about this like 2 rivers flowing in opposite directions. The gas from 3I Atlas is flowing toward the sun at about 200 ms. The solar wind is flowing away from the sun at 500 km/s. That is 2,500 times faster. At some point, these two flows are going to collide, and the gas from 3I Atlas is going to get stopped and swept backward. The calculation involves something called ram pressure. Ram pressure is just the force you feel when something moving pushes against you, like when you stick your hand out of a car window. Loeb used measurements from the James Webb Space Telescope showing 3I Atlas is losing around 500 kilos of gas per second. When you plug the numbers into the equation and solve for where the pressures balance, you get a very specific answer. The gas should stop at about 5,000 km from the nucleus. Now, 5,000 km might sound like a long distance, but in space terms, it is incredibly close. 5,000 km is roughly the size of the glowing cloud around 3I Atlas that we see in Hubble images. That bright fuzzy halo is called the coma. So what Loeb is saying is this: if 3I Atlas is a natural comet, then gas can only stream about 5,000 kilometers away from the nucleus before solar wind sweeps it backward. Beyond 5,000 kilometers, the anti-tail should only contain dust particles, no streaming gas. This is a clean, testable prediction. You can actually measure this with telescopes. Now, here is where everything gets interesting. The anti-tail jet we are seeing in images extends for hundreds of thousands of kilometers. Some observations show it reaching 400,000 kilometers. That is 80 times longer than the 5,000 kilometer limit. So, the big question is, Does that jet contain streaming gas all the way out to 400,000 kilometers? Or is it only dust particles beyond 5,000 kilometers? If telescopes detect gas molecules like carbon dioxide or carbon monoxide streaming along the entire length of that jet, then something is seriously wrong with a natural comet explanation, because physics says that gas should have been stopped by solar wind at 5,000 kilometers. If telescopes only detect dust beyond 5,000 kilometers, then 3I Atlas is behaving like a natural comet. Now let's talk about what happens if the test shows gas streaming way beyond 5,000 kilometers. If that happens, then we have to ask what could possibly push gas that far against the solar wind. Loeb calculated what would be needed. If the gas is being ejected by some kind of propulsion system instead of natural sublimation, then the exhaust velocity determines how far it can reach. Chemical propellant thrusters have exhaust speeds around 5 km/s, allowing gas to reach about 25,000 kilometers. Ion thrusters can shoot exhaust at 90 km/s, allowing gas to reach about 100,000 kilometers. These are three completely different signatures that telescopes can distinguish. Natural sublimation gives you 5,000 km maximum. Chemical thrusters give you 25,000 kilometers. Ion thrusters give you 100,000 kilometers. This is why Loeb is calling this a definitive test. The prediction is clear, the observation is measurable, and the interpretation is unambiguous. Now let's talk about why dust behaves differently. When gas drags a dust particle sunward and then gets stopped at 5,000 kilometers/meter, that dust particle keeps going. It is like throwing a bowling ball. It coasts on its own momentum. A 10-micron dust particle is about 8,000 times more massive than a typical submicron particle, giving it much more momentum. It can travel hundreds of thousands of kilometers before radiation pressure finally brings it to a stop. But if gas is streaming alongside that dust all the way out, then we have a fundamental problem. Finding gas beyond that point would mean either our understanding of solar wind physics is completely wrong, which seems unlikely, or there is an additional force acting on the gas that we are not accounting for. The only force that could push gas that far is active propulsion. Avi Loeb analyzed 17 different images from the Hubble Space Telescope using a Larson Sekanina rotation gradient filter. What the processed images revealed is striking. Within about 24,000 km of the nucleus, 3I Atlas is producing three separate jets with perfectly symmetric angular distribution. The jets are spaced exactly 120 degrees apart. Think about a circle divided by 3. These jets are equally spaced like the hands of a clock pointing at 12, 4, and 8. One jet points roughly away from the sun, and the other two point sideways. Natural comets produce jets from random pockets of ice. There is no reason those pockets should be spaced exactly 120 degrees apart. Ice distribution is usually irregular, but three jets spaced in perfect 120 degrees symmetry is a geometric regularity that is very unlikely to occur by chance. Now at larger scales, the structure is dominated by the big anti-tail. That 10:1 ratio tells you this is an extremely tightly columnated beam. Normal comet tails spread out. This one stays focused like a laser across 100,000 kilometers. For that level of columnation to happen, the jet has to stay aligned with a specific direction precisely. Loeb explains that this requires the rotation axis of 3I Atlas to be nearly aligned with the direction toward the Sun. If it were misaligned by more than a few degrees, it would get smeared out as the object rotates every 16 hours. The fact that it stays tight tells you the misalignment is less than 6 degrees. The probability that the rotation axis would be aligned within 6 degrees just by random chance is only 0.2%. That is 1 chance in 500. So now we have two separate geometric anomalies. First, the three inner jets are spaced in perfect symmetry. Second, the rotation axis alignment has only a 0.2% probability. When you combine these two, you are looking at a configuration that seems almost designed. Loeb is careful to say this could still be natural. Unlikely things do happen. But the alternative interpretation is that these jets are deliberately configured. Are they technological signatures, or can they be a natural outcome of gas dynamics? Telescopes can use spectrographs to detect molecules like carbon dioxide. If the gas signal drops off around 5,000 km while dust extends much farther, that confirms the natural model. If gas extends hundreds of thousands of kilometers, that is a major problem for the natural explanation. The telescopes that can do this include KEK, the Very Large Telescope, ALMA, James Webb, and Hubble. And the observations are happening right now. The International Asteroid Warning Network is running a planetary defense campaign as we speak. Natural jets driven by solar heating should pulse on and off and shift direction as different ice pockets face the sun. Technological jets would show much more stability and control. If the jets are maintaining fixed global orientations that do not match the rotation pattern, that would be much harder to explain naturally. Have we ever seen anything like this before? Anti-tails in comets, like Arend-Roland or Hale-Bopp, turned out to be optical illusions from specific viewing angles. With 3I Atlas, the structure has been persistent for 6 months, which is much harder to explain as a trick of perspective. We have also never seen a comet maintain jets in perfect 120 degrees symmetry or a rotation axis locked onto the sun direction for months. The combination of all these things is what makes this so interesting. If it turns out that 3I Atlas has propulsion, it would be the first confirmed technological object from another star system. But even an exotic natural explanation would advance our knowledge of fundamental physics. Another major milestone is coming up on March 16, 2026, when 3I Atlas makes its closest approach to Jupiter. The object will pass at about 53 million miles, which is almost exactly at Jupiter's Hill radius, the ideal location to release satellites or probes into stable orbits. Finding an interstellar object arriving precisely at this distance has only a 1 in 25,000 random probability. Scientists are preparing to watch this flyby very closely for any course corrections or object releases. We are about to get answers. Within weeks or a month or two, we will know whether the gas extends beyond 5,000 kilometers. Whether 3I Atlas passes this test or fails it, our understanding of the cosmos is about to change. If you watch to the end, please click the like button and let me know your thoughts. God bless you and have a great new year.